So I was tasked with the job of giving sort of more elementary lectures on going from our usual description of electrons in a solid to quantum spin models, and then describing what is meant by frustration or geometric frustration in these spin models, and then talking about some unusual phases and behaviors that can arise in these models. So I'm going to try and do things at roughly the level of a graduate class at least my institute. If that's too slow for some of you, I'm sorry, but that's how I've read it. So let me start with just reminding you that when we learn solid state physics, we usually start by talking about band theory. So we have, move it up, okay, like so. Yeah, okay, there, yeah. So usually when we start learning solid state physics, we talk of an electron that sees some potential coming from the nuclear cores and the core electrons around it. And this is a wave that's seeing this potential and going. And we learn to solve the Schrodinger equation in some approximation in this periodic potential. And that's the subject of band theory. And for example, if you have this toy model of a one-dimensional solid, you're taught that the eigenstates or the wave modes of this electron wave are labeled by a crystal momentum, which goes from minus pi over a to pi over a, and then it has some energy eigenvalues and so on. So then our job then is to use the notion of Fermi-Dirac statistics, the idea that only one electron of a given spin polarization can occupy one of these states, and say what the zero temperature ground state is. So you start by filling things until you've got to the last electron, and each of these orbitals now has two electrons in it, one up, one down in spin polarization. And if you have your electron count that in such a way that you've half filled some band, then you learn that electric field will tilt this band structure and allow current to flow. If it's fully filled, then there's no current flow. And that's how we understand metals and insulators in sort of usual band theory. Now this is what I would call sort of the wave picture. Of electrons in a solid. And one can contrast it with what you would call the particle picture, which is to focus on the fact that electrons are after all packets of charge, and they repel each other, and like all like charged objects, they would like to be as far away from each other as possible. And so now if you have some array of sites which are sort of the cores on which the electron would like to sit, if there's one electron sitting here, the electrostatic repulsion of this electron with other electrons suggests that the other electrons would like to be as far away as possible, would like to sit on a different core. And this then becomes a sort of a classical problem of placing charges on some sites in such a way that you minimize your Coulomb repulsion. And so this I would call the particle picture. And of course, the real answer is that you have to take into account both these effects, and band theory leaves out Coulomb repulsion. This completely leaves out quantum mechanics. And to do a full job of what happens at low temperature in the electronic solid, you must have a method that tries to incorporate both these pictures, right? And you could start with band theory and add Coulomb repulsion in perturbatively. And that's the whole elaborate subject of many-body perturbation theory that you typically take a class in grad school. But there is also sort of a converse point of view, which says, let's start with this picture and put the wave nature back in, put the quantum mechanics back in. And that's more of a strong coupling expansion. It starts with the idea that Coulomb repulsion dominates, so that these electrons really behave like classical particles trying to stay as far away from each other as possible. But of course, they are not classical particles. They have tunneling amplitudes for tunneling to other configurations. and one must systematically expand in the effects of those tunneling processes to ask what happens at low temperature. Right? So that's a complementary kind of perturbation theory, if you wish, from the standard one that we learn in grad school. And that is what we'll focus on here today. The goal is to start from this picture, put back in quantum mechanics, and derive what is the low energy effective Hamiltonian that describes the system at very low temperature. Okay? So, sort of the goal here is to get to the point where we have a description in terms of the electronic spins alone. And the case we are going to take up first, and pretty much the only case we'll discuss in detail, is the case where you have a half-filled band. You have a single band, the other bands are very far away, so you forget about it. So there's one orbital per site that you worry about, and you're exactly at half filling, which means the number of electrons in your system is exactly equal to the number of orbitals available. Why do I choose this? Because it's the most dramatic example for showing sort of the difference between this wave way of thinking and this particle way of thinking. Because in this standard band theory or wave picture, if it's half filled, these are the states that are filled, the rest are empty. And we are talking of the one band approximation, so the upper band just doesn't exist for us right now. And this is exactly what in band theory you would consider a really good metal. It's got a big Fermi surface, and any small tilt produced by an electric field will immediately make current flow. Right? On the other hand, in the particle picture, you can see that since I have exactly the same number of orbitals as the number of electrons, I can place, and I want to minimize the Coulomb energy. The lowest energy configuration will be you place one particle on every orbital. Right? What is left free is the spin degree of freedom of each electron. Each electron has two spin polarizations, so you have two possibilities, and that's the freedom at low energies. There is no freedom for particles to move freely, because if you try to go here, you pay this enormous Coulomb energy. And so in this particle way of thinking, this is the situation in which you would least expect to carry current. It should be a pretty good insulator is what we would say, right? And which sort of is the correct way of thinking depends of course on the size of the Coulomb repulsion compared to the kinetic energy. Right? And so we are now going to work in the limit where the Coulomb repulsion is much bigger in its effect at low temperature than the kinetic. And we are going to work in this so-called Hubbard model limit or approximation. So Hubbard was the first historically to capture both these tendencies in a single simple Hamiltonian that you could write down and try and analyze. So let me write that down. So you write this down as a sum of hopping terms on links of whichever lattice you're on, nearest neighbor links. These are the tunneling amplitudes that allow electrons to be destroyed at a site and created at the next site without changing the spin polarization. This is the kinetic energy. And then we keep the simplest sort of term that represents Coulomb repulsion. We only worry about Coulomb repulsion on the same core and don't worry about the long range part of it, which we assume has got screened out by the other electrons that get involved. So I'm writing this in standard second quantized notation. These are creation and annihilation operators, and this is the number operator that tells you how many particles of up polarization there are at site I, how many of down. And of course, this term is non-zero only if a site is doubly occupied. There's an electron with spin polarization up and an electron with spin polarization down at the same time. So if you have two particles like this at a site, it costs you energy U. If you have only one particle like that or like that, it costs you nothing. That's sort of the the effect of this term. And of course, you can, if you like, work in the grand canonical ensemble by adding a chemical potential term that would couple to the total particle number. But it's much simpler in what we are going to do to work in the canonical ensemble and just specify how many electrons we have relative to the number of orbitals. And that's anyway how you would proceed in a real material, because from chemistry you would know how many valence electrons there are, and that's what you would start. Okay. So this is the setting, and as we've just said, at low, if U is much bigger than T, at very, very low energies, which would be of relevance to low temperature experiment, there's going to be no current that can flow if you apply an electric field, simply because Coulomb repulsion will just block electrons from hopping to neighboring sites. And all the low temperature physics will be the physics of localized moments that live on individual cores, right? That will be the physics. And that physics will not happen at energy scale U or at energy scale T. They both drop out. And it's going to be an energy scale that's generated perturbatively by honestly doing a perturbation theory that takes this as the perturbation and this as the bare Hamiltonian, which is the exact opposite of what we do in standard many-body perturbation. So, any questions so far? Okay, good. So now, we'll set this perturbation theory up. I'm not used to lecturing in such a big room. So is this too big, too small? It's legible? And can I go all the way there? Or not the last board? Okay, good. All right. And not the first either? Okay. All right. So then let me do some problem. So one immediate difference from standard many-body perturbation theory that you would have noticed is that usually we start with the Fermi surface as our ground state and then do perturbation theory in interaction. So there's unique ground state specified by the Pauli exclusion principle and the band structure, and then we start calculating the effects of electron-electron interaction. Here, we don't have a unique ground, right? In fact, the ground state has degeneracy equal to where n is the number of orbitals, also equal to the number of electrons. That's because each electron can be up or down. So what you're not going to be able to do so easily is work out shifts in energy. So you should work so you should divide your work up into two pieces. One is to derive an effective Hamiltonian that, if you could diagonalize, would give you the eigenvalue. And then the second question is, what are the eigenvalues and eigenvectors of that effective Hamiltonian, right? You have to split it up into these two jobs, because this itself is a macroscopic degeneracy, in the sense that the log of this scales with the volume. And so there's no way you're going to actually start calculating energy levels, right? Which is the standard thing you would do. What you instead do is derive effective Hamiltonian that describes this low energy field, right? And that effective Hamiltonian will be your quantum spin model that then you develop approximation schemes to develop understanding. Okay? So today we will try and sort of go through the standard derivation of the Hamiltonian that emerges when you do this perturbation. Okay? And the way to do this is to sort of imagine that your original Hamiltonian is some very big matrix, with lots of entries, and then you want to do some sort of change of basis. You want to do a canonical transformation that rotates the basis, so that the rotated Hamiltonian has a block that corresponds to these 2 to the n states, and then a block that corresponds to everything else. And at least to a given order in perturbation theory, we want to set the off-diagonal block to 0. If you can find such a canonical transformation that does this, then you can focus on just this matrix. Right? This is the matrix that's supposed to describe your 2 to the n levels. And forget about all the complications of charge motion that are in this other sector. Right? So you can separate the problem into spin physics and charge physics. Right? If you can find such a canonical transformation. So H tilde is the transformed Hamiltonian. Right? And our goal is to find this effective Hamiltonian by doing this canonical transformation. Of course, we can't do it exactly, so we do it order by order in perturbation. So this is what's called Van Vleck perturbation, and it's particularly suited to these large degeneracies. So let's try and set this up and then use it today. So to set it up, we write and I'm going to use some notation where the projector onto this spin part of the Hilbert space, I'm going to call P naught. So P naught projects onto that, and Q naught is going to be the complementary projector that projects onto everything else. Okay? So the full Hilbert space is the sum of these two. And so if we can do this rotation, then just to say in a formula what I've been saying in words, the effective Hamiltonian we are interested in is going to be that's what we want. Yeah. So how do we determine this canonical transformation? That's the first task. So let's sort of take the general problem where you have H equal to some H naught plus some P, right? And let's stick a lambda in front of this just to count powers. In the end, we are not really going to have anything like that. What's going to play the role of lambda is of course going to be P over U. It's going to be like that. But let's just stick this in as a formal parameter to count powers. Okay? So of course you can write down a general expression for this in terms of sort of a iterated commutator expansion. So let's write that down first. So let's write and so on. Right? You can write this power series down as iterated commutator. This is a standard identity that you can derive for yourself. So what we want to now do is use this and count powers of lambda by imagining that W is expanded itself as a series. So of course when lambda is 0, there's no need for a rotation. So it starts at order lambda to the power 1. And what we need to do is determine W order by order and stick it back into the formula for H tilde to a given order and work out the effective. That's sort of what we are after. Right? So let me, so of course I don't want to do this whole thing in great detail for you, but I do want to give you some intermediate formulae to make the final result believable. Right? In the tutorial, we can fill in the missing steps. So the first point to note is that this doesn't completely specify the effective Hamiltonian. You can easily see that just saying that I want to do a rotation that splits this off from this is not enough to specify what the canonical transformation is. Because of course, once you've done this, I can do all sorts of rotations inside this block and all sorts of rotations inside this block, and that don't change this structure. That means W is not unique. And there's many flavors of this perturbation theory which differ from each other, roughly speaking, by the choice of prescription you use to define W. What choice do you make? The one that in many textbooks, let me just say what it is to say that you actually don't write it just like this. You take your H naught and you classify the Hilbert space based on eigenstates of H naught. So H naught will have different eigenstates. Let's label them by n. So this is n equals 0. So there will be some group of states which are eigenstates of H naught, which are closely spaced. Then the next group of states, n equal to 1, then n equal to 2, like that. And one complete prescription for W is to say that W must not have any at any order in perturbation theory, full W, order by order, must only connect different blocks of eigenstates of H naught. Okay? And if you did that, then you've actually done more than what I described. You further split this Q naught into many different blocks, each corresponding to other groups of eigenstates of H naught. I mean, in this Hubbard model that we are talking about, this would correspond to 1 W occupied site, 2 W occupied site, 3 W, and so on the whole lattice. And then you would have derived the effective Hamiltonian that doesn't couple different sectors at all. So it only talks within the sector of a given number of W occupied, right? All matrix elements would be between different states having different numbers of W occupied sites would be split. And then you would, in one go, you would have derived an effective Hamiltonian that not only discusses the spin physics at very low temperature, but also discusses the physics of excitations. So you could describe the physics of doublons, the 1 doublon sector, the 2 doublon sector. Doublon is simply fancy modern language for 2 particles at a time. So you could describe all these sectors with 1 half. Now that turns out to be actually quite painful to do the calculations with. So we are going to do a much more limited thing. We are just going to break it up like this without further breaking it up. And so this is not the prescription we are using. So the prescription that I found most convenient to derive this standard results of quantum spin Hamiltonians is to say that this is a much stronger condition on W. It says all matrix elements of W within the first block are 0 and within the second block are 0. So in particular, W can't even have matrix elements that couple the n equals 1 with the n equals 2 sector, for example. So it just cannot have any matrix elements in that sector. So there's a much stronger requirement on W. But as I'll show you, you can actually satisfy it order by order in W, and it actually makes the calculations go much faster. So this is the choice we are using. It's one of the many choices you could use. Sorry, I thought I did. So Q naught is the projector onto everything else, right? So P naught is the projector onto the spin subspace P naught. The point is you don't try to do all your work at once. You just work out the effective Hamiltonian. So you don't care to do any rotations in the other subspace to block diagonalize it. And that's what this says. Okay. So with that choice, things simplify. And the reason they simplify, roughly speaking, is because each of these nested commutators really describes the physical process in the effective Hamiltonian, where you start from one of the ground states, one of the 2 to the n states, make a transition, make another transition, and then come back to the ground state. That's how you derive it. So these are all virtual fluctuations you keep track of, and you come back down to the ground, right? So by making this condition, what you ensure is that if you made a transition to this other subspace where there are doublons, the next transition must bring you back. And that severely limits the number of possible terms you can write. And that's what allows you to go to 4th order in one lecture. So that's the choice we make. And so with that choice, now let me sort of tabulate some basic formulae that I'm going to use. Yeah. This is a general statement, but it would only be useful if you want to, for example, just study the 2 doublons. Right? So you break it up into the 2 doublon sector and everything else. So you don't simultaneously derive effective Hamiltonians for each sector. You pick one and derive an effective Hamiltonian. Right? Because in the other sector, in the complement, your effective Hamiltonian will not be block diagonal. It will be a big mess. So you don't even look at it. That's the advantage. You do less work, so you can do it faster. So is this part of the board visible to everybody? Up to there, right? Okay, so let me tabulate what I want. So to order lambda to the 0, I simply have H naught. Lambda to the 1, I have V plus I square lambda cube. So I'm just writing these out once and for all so that you can check that you do get the answer I'm quoting, even if I don't derive all of it here in front of you. And I'll spare you the 4th order term, we'll write it down if we need it. This we'll just use. Can you see the end of it? Well, anyway, I'll read it out if it's needed. Okay. Sorry? So lambda 3 third term, W1, W2. Sorry, I need to complete that. Right? Is that right? Yeah, that's right. Sorry? Plus. So now I'm just going to illustrate the procedure by doing the first couple of orders and we'll write down the answer. So if you wanted the effective Hamiltonian first order, you would simply take the projector of V. In this case, V is just our hopping amplitude, and clearly you cannot hop without going out of the one particle per side sector. So this is just 0. The first non-trivial term will come from H2. So let's write down what H2 would be. So if you look at that formula, to get H2, you need to know W1, right? To get H2, you would need to know W1, and that you can get by imposing this condition we talked about, that the effective Hamiltonian has to be off block diagonal, right? So we can write the other way around. This is just a bracket, not a commutator. We write it like that. So this means that W1 is specified now by solving this equation. And the actual formula is something you can work out easily. So you can plug that back into the formula for the rotated Hamiltonian and get the second order effective. Then you can work out W2 by taking the relevant equation here and imposing the same condition that says you must not have any matrix elements between P0 and Q0 for the effective Hamiltonian, right? Since you already know W1, that becomes an equation for W2, which you can solve, and so on. And so there's a little bit of algebra to be done, which I don't think I should do in the main lecture. We can do it in the tutorial if somebody wants. So let me then, following this through faithfully, you should be able to derive today evening. Somebody's laughing. Well, I did it. Okay, takes one afternoon. So you can derive the following formulae for the effective Hamiltonian up to fourth order. So let me write them down. So the effective Hamiltonian So my notation is I'm writing down each order separately. So as we said, and let me define R0 for you in a minute. finally, so R naught is simply this projector Q naught divided by E0 minus 3. Okay, it's the energy denominator, minus of the energy. So the physical interpretation of these things are fairly straightforward. To second order, for example, you start with a state which is minimally, minimum energy for H naught, which has no doublons. And then you act with the perturbation to go outside that no doublon sector to one of the excited states. That's a virtual fluctuation. And then you come back down. Okay, that's just described second order perturbation. To third order, it's the same thing. The main point to note is that you go from the ground state sector, I left out, yeah. You go from the ground state sector to some excited state, then you go to another excited state, and then you come back. You do not come back to the ground state. And at fourth order, there's an obvious generalization of this, which keeps hopping between excited states, three excited states, and comes back down. But then there's also terms that come back down in the middle to the ground state. Okay. So the full effective Hamiltonian at fourth order involves two kinds of processes. And actually, when we work out ring exchange terms in the effective Hamiltonian, there's a cancellation between them that gives you the correct. So that's the formula you can derive starting with that. And it's not particularly, yeah. P naught V P naught, that's right. I'm using, so this is, so for the third order, this is special to the case where this is 0. That's right. Otherwise, there's one more. That's right. In our problem, that's true. So I've written a. Yeah. So this is just the projector to all the excited states, and E naught is the ground state energy, and H naught is whatever is the energy of the excited state you're at. Right. H naught is the. Right. So I've taken the case where they are. Otherwise, there's sort of a harmonic mean that comes of the E naughts acting on both sides. Right. So I'm sort of, I've reduced the formulae to whatever I need for this lecture. But there is otherwise, so if all the E naughts are not the same, then you get kind of a harmonic. You can work that out. Okay. At second order, that's obvious from standard perturbation theory itself, but it happens to be true at higher orders. So now our goal is to sort of use this to work out what happens to the spins in the low energy vector. Right? That's what the real lecture is about. Yeah, yeah. I could have written down, yeah, so here the symmetry consideration is trivial, right, it's SU2. But then you need to know what are the terms you get with SU2 symmetry, right? Sure, but you want to know, for example, things like what's the magnitude of sort of ring exchanges relative to, so this is a question now of ground states, and so part of the reason I decided to do the whole calculation is that in many examples of frustrated magnets we know, the actual ground state is somehow seems to be at some threshold. There's a very delicate balance of energies, and for a given system, the answer could go either way depending on small changes in some terms. So it's good to know what the terms are. So this is sort of the exact opposite of Shubro's point of view, which is useful when you have very complicated possibilities and you want to at least classify what do the terms look like. Here we know what the terms will look like, right? There's nothing more to it. We just want to know what the numbers are. Right? In fact, in the evening tutorial, Shubro has promised to continue with his point of view and tell you what the effective Hamiltonian is for those complicated. So, all right. So let's sort of do the first thing, which is Heisenberg exchange. So I don't need this. So let's take a two-side problem. I have an electron here of some polarization and another one there. And I want to know what's the effective Hamiltonian that governs their spin physics, right? And this is a calculation Heisenberg did in 1920 something in some slightly different context. But we are going to do it just by taking this formula and asking what terms arise. So our V, what we've been calling V, is minus T right? So hopping of electrons of both species. Now these are electrons, so there are signs that come from exchange of particles. That's the whole point of Fermi statistics, right? And you can keep track of the sign in two ways. You can actually just do the algebra using this operator notation for all the perturbation theory. And then you have to be careful to anti-commute operators to get the right minus signs. Or you can think physically in terms of which particle went where and whether the same particle came back or there was an exchange. So you can either count exchanges, that's sort of a physical way to think, or you could just do anti-commute. So just in this one case, let me sort of do both and show you how the two match. So let's first act with, so let's have some notation where T12 is the destruction of a spin of an electron at site 1 and the creation at site 2. So it goes from 1 to 2. And T21 is the opposite term. So obviously from that formula you could see that I should first act with either T12 or T21, it doesn't matter which one, I'll get a factor of 2 in the end. So let's act with T12. So I have to take this electron and put it there. That would be the physical way to think. But what I'm really going to do then is right. This is the first action in that formula. I will start with the ground state. I will act with the perturbation, right? Now, I should be clear if I'm doing this second quantized operator notation, what I mean by this. What I mean by this is I start with the vacuum with no particles, and then I have some pre-specified convention that orders the sites, and I act with creation operators. In this case, my convention is to read it from right to left. So I act with these creation operators. And this is the state sigma 1, sigma 1. If I acted with the creation operators in the other order, I would get the same state except for a minus sign. That's the fermion minus, right? So this is what I mean by this. So keep that in mind. And now I act with this. So of course, so this is a sum over sigma. The only term that can act is when sigma equals sigma 1, right? Now, if sigma equals sigma 1 and sigma 1 equals sigma 2, if they're both up, let's say they're both up, then nothing can happen, and the effective Hamiltonian just cannot couple two up to anything else, right? So that we. So let's take the case where one of them is up and the other is down. Okay. So now, because I'm destroying a particle, this must be up. So when I do that, Since this was anyway the last creation operator to have acted, I can just destroy it. This becomes P12, C dagger 2 up, and there's no particle here, so I have not acted with that creation operator, and there's sigma 2, which in this case is down. Right? So now I could just, so I've got this state. Now I have to act with one more perturbation and come back to the ground. So now having done this, I'll get a state which is, I have two particles at site 2, right? Now when I act again, I should act with T21. Now when I act with T21, I can do two things. Let me just erase this. So I've got this state, and I have to act with T21. Right? If I destroyed, so if I destroyed the up spin, then I'll end up creating it back where it was. There's no further anti-commutation, and I not get any sign there. On the other hand, and that would not change the state. So that would be an amplitude for going from up down to up down. That would be the amplitude in the effective module from just doing that. And there'd be no net sign coming from the anti-commutation, right? Which is consistent with the idea that one particle, so you had up, down, you hopped this particle there, and then you hopped it back. So there was no exchange of particles physically, consistent with the fact that there's no sign. And so there would be no sign coming from the exchange, but there would be a sign coming from the energy denominator, because all our energy denominators are negative. So you would get this amplitude is minus T square over U. Okay? And you can do it in two ways. You could either first hop this particle here and then back, or hop that particle there. You would get a factor. On the other hand, at this step, you could destroy this spin and then create a downspin at the other. Physically, that would correspond to an exchange. You would bring this particle back. Physically, it corresponds to an exchange of particles. In the algebra of anti-commutation, what you would have to do is you would need to anti-commute this through this to destroy it. That picks up an additional minus sign. So this process, the exchange, comes with a plus 2t square. Okay. So that's all we need to work out the second order effective Hamiltonian. And a convenient way to sort of write everything down is to define a spin exchange operator which, acting on two spin labels, exchanges them. Okay? You can check very easily by using your standard algebra of Pauli matrices that this is a good representation of P1. Okay? So one convenient way to capture both those amplitudes is to just say that I have so you see when I exchange, I should get a plus sign in this case, and the diagonal guy should be that, right? So you need to subtract a minus 1 so the diagonal guy works out right. So H effective becomes 2 T square over U P12 minus identity. So that's the Heisenberg exchange Hamiltonian for the leading order perturbation theory. for this Hubbard model. How did I jump from just a two-side problem to an effective Hamiltonian? Well, I realized that at second order, the perturbation theory knows only about two sides at a time. So I could do exactly this on any bond of the lattice, of whichever lattice I started, right? So my effective Hamiltonian to second order clean the board up, or it will write it down here. This is notation for nearest neighbor links of my lattice. This is not visible? Okay. Let me use that one. Yeah, it's kind of bad. This white is better. Sum over all links of the lattice, exchange operator minus ID. Right? And if you think about what we've actually derived, this is just mod square. Right? Because you went P12 and came back P21. Okay? So no phases. Now we could do the same thing to higher orders. And to third order, there's actually a simple argument that says there'll be no term unless the hoppings enclose a flux. And but we do want to consider the case where there is flux. I'll explain why. So let's work out the general form to third order. So to third order, I need this. So it's exactly the same as the second order calculation. I'll start with a state. I'll go to an excited state. I'll go to another excited state. Then I'll come back. And at each point of time, I'll pay an energy cost. Right? That's the formula that we want to use. I think I should just clear the board at this point and start drawing pictures. So now we are not going to bother to do this sort of painful algebra of anti-commutation. We are just going to keep track of which particle went where and where the particles finally ended up. And we are going to count the number of interchanges between particles to decide what's the fermion minus. Okay? So I've got site 1, site 2, site 3. And again, this is imagined to be embedded in the whole lattice. So this applies to any group of 3 sites which are all talking to each other by hops. Okay? So if there's triangles in the connecting, this is P12, that would correspond to a particle going like that, and the reverse process would be 1, 3, 3, 2, 2, 1. And we are going to allow for an orbital magnetic field so that the product of these 3, so P12 is going to be e to the times some flux times just some PQ, and the other way, what did I do? 1, 2, 2, 3, 3, 1. Okay, 1, 3, 3, 2, 2, 1. And we're going to ask what's the term that you get to third order. This is perhaps the first non-trivial application of that machinery. The second order formula you could have derived in all sorts of ways in 2 minutes. Yeah. So, I mean, these are electrons and they are hopping on some lattice. And if there's a external magnetic field, there can be, there's a corresponding vector potential that the electrons are sensitive to. And they pick up a phase every time they move. And when they move and come back, they will have picked up a phase that's equal to, in the right units, the flux of the magnetic field through the loop they moved. In second order, we didn't go to a loop. We went and came back, right? So here there are loops possible. First loop you can have is 3 links, right? So that's why this is the first time you discuss. Yeah. So it just has to be this, right? And the simplest way I know where this comes in is if you have a layered material and you apply a perpendicular magnetic. But of course, you can imagine these synthetic systems of cold atoms where you can rig up hopping star phases and so on. And then this would be one of your synthetic gauge fields, the flux of one. So of course, you can still have second order contributions here which are already accounted for by that. So we want to work out the actual thing that involves all 3 bonds. So the basic rule of the game is that whatever term you write down must involve one action of a hop on this bond, one action of a hop on this bond, and one on that bond. Now you can easily see that if you want to return back to a ground state in 3 hops, using all 3 of them, they must all be taken clockwise or all be taken anti. There's no other way to do it, right? Because if you went and came back, you would not be able to go to the ground state when you acted again, right? So basically we're looking for all processes by which a particle moves anti-clockwise or clockwise. And so there's many ways in which this can happen, and we have to just look at each of them and ask what the final state is and how many particles, how many pairs of fermions got interchanged in reaching that final. So number of pairs of fermions that got interchanged will give you the number of minus signs, and then the rest of it will just give you the answer. Right? So this is a sort of a nice counting problem, which we can do in 5-10 minutes. So let's do that. And the answer we derive is interesting, so let's do that. So let's first look at all the anti-clockwise processes. Right? That means I have to take all hops this way. 1, 2, 2, 3, 3, 1. Okay? So, and so you want to be able to write down a general effective Hamiltonian. So part of the choice you have to make is what is the initial state you want to start with, and what amplitude do you want to look for contributions of, right? So let's look for contributions that go, so let's start with this state. This is just a choice I'm making. Start with this state of 3 spins, and I look for 3 kinds of amplitude. I look for amplitudes that keep it invariant, or take it there, or third one is supposed to take it there. So I could end up with this, I could end up with this, or I could end up with this, starting from that. Okay? So I want to see what are the contributions to each of these, right? So let me just draw some pictures. So let's say first this particle hops here. So if I'm going anti-clockwise, clearly I can't do this to begin with. That's blocked by Pauli exclusion. I can either start with this particle coming here or this particle going here. So let's start with that. Okay? So this takes me using a T12 Now I can take the same particle around there using a T23. And I can bring it back. This is the trivial thing where one particle just went all wrong, right? So there's no exchange of particles clearly. And this must contribute to the coefficient of identity, right? Important thing to remember is that there's no exchange, right? Now at the last step, I could do something else. Here, this step, right? I could, instead of this particle hopping there, that one could, right? So I could also get and in effect what you've done is you've exchanged two particles. Right? Yes. So you can define new electrons that are particle hole conjugates of the old electrons, and you can take your original Hubbard model in this particular one band case and remember that you're at half distance, and when you make that transformation you will see that you've left the Hamiltonian plane, and therefore the answer must have T going to minus T symmetry, and therefore there can't be odd order terms, right? But that's not quite the whole story, because when there are fluxes you don't have that. Okay. So this involves one exchange of particles, which I'll write like this, right, in brackets. And it contributes to that amplitude, where I moved this there. Okay. Now the important thing to note, I don't want to go through all the processes, the important thing to note is that for every such process that involved an exchange and that sent the downspin up by going anti-clockwise, there is a clockwise process that involves two interchanges. Okay? That involves two interchanges and achieves the same function. Okay? And they interfere with each other, and if there was no flux, the clockwise would equal the anti-clockwise and you get it. This is the important thing. So let's find that clockwise process, and then you will see how things happen. So let me look in my table for the clockwise process, the partner of this. I think that's the one. So you do this. So you first hop this particle there. Right, this one went there. This was a 3, 2. No, 3. No, 1, 3. 1, 2, 3. 1 to 3. Then you hop this particle there. And then you hop that particle here. Okay. Clearly, this didn't involve an interchange of two particles. This involved actually a ring exchange of three particles. 1 went to 2, 2 went to 3, and 3 went to 1. Not in that order, but in effect that's what they did. Right? So this has a x, 1, 2, 3 permutation, right? Which, as you know, can be written as a product of two interchanges, x12 and x23, right? So there's no minus sign coming from fermion interchange in this process because there's two interchanges, whereas there is one there. And all other factors are the same, right? Except for that one minus sign. So that means these two things interfere with each other. So you get things like T12, T23, T31 minus right? So this is the imaginary part of the product. And remember, the product has a phase e to the I pi, so there's a sine phi that comes. And so this is the important thing. the orbital magnetic field couples to these amplitudes that hop in lengths. Otherwise, the third order term is 0. Okay? So if you now go through this exercise, in detail, you can find partners for every process like this, and you can then derive what the final effect at Hamiltonian is. So let's write that down now. So let me explain what these are. So these are operators that are defined as things that act on these spin labels and do a ring exchange on them. So this goes to sigma 3, sigma 1, sigma 2. And the conjugate is the opposite process. So in terms of these operators, you can write down all your amplitudes by this formula. So the important thing is that although you might imagine that the charge degree of freedom is frozen and it's only the spin physics that matters, an orbital magnetic field still can have an effect if you're not very deep in the insulating regime. If the charge gap is not too large, if U is not too large compared to T, if these T cubed over U squared terms matter, then you can still have effects coming from the orbital magnetic field, and the effect has the form of this sort of three particle ring exchange. Now, of course, you can sort of look at the algebra of angular momentum operators, and since we've already written P12 as 1 plus sigma 1 plus sigma 2, you can use the identity that you can implement P123 by first doing P12, well, I think by first doing P23 and then doing P12. So this is just an identity of permutation operators, and we know formulae for each of these. So you can plug that in and you'll get an explicit formula for P123, and you will realize that that can be decomposed into sums of exchange. So this is actually just a way of collecting all possible exchange terms, two particle exchange terms together. So let's write that down. So P123, if you work out the, just do a little bit of algebra with the sigma matrices, is P12 plus P23 plus P31 minus identity So P123 has a kind of a real part and an imaginary part. And it's the imaginary part that's playing a role in our answer. Yeah. No, so I'm sending one, so this label went here, this label went here, that label came here, right? So how would I implement that as a product of two interchanges? I would first interchange these two labels, then I would interchange those two labels, right? This is the correct formula. Just thought of as permutation operators, that's the algebra. Yeah. Yeah. So of course the Zeeman field we can, because of SU2 symmetry, put back in at the end, right? It's always just magnetic field times the total spin operator in the Z direction. But you can try and do it with the, I mean, we know what that does, right? You just couple the net spin in the Z direction to B, that's the Zeeman term. But the important thing is that there is an orbit. And so since it's the imaginary part that matters, we can rewrite this. As coupling you see, this is some sort of chirality. It says whether spins 1, 2, and 3, thought of semi-classically as unit vectors in some direction, define a left-handed or a right-handed triad, right? So the statement is that the orbital magnetic field, so I forgot this sign phi, all important phi. The orbital magnetic field, the flux of the orbital magnetic field couples to the spin chirality. And I don't know if Subi is going to talk about organic triangular lattice magnets, but this is supposed to be important to the physics of those systems, because they are systems where the charge gap is not so very huge, and these higher order ring exchange terms matter. Okay, so that's the third order answer, and I think I still have 10 minutes. So let's now go to the next order and ask what new things can come. Okay. So now at fourth order, it's kind of convenient to characterize all the possibilities into terms that involve only one bond, terms that involve two bonds, and then terms that involve four bonds. Okay. So if you just involve one bond, right, remember our formula for fourth order has two kinds of processes. One is you go from the ground state manifold into an excited state, then keep going into excited states till you come back down, right? If you just have processes that involve one bond, that's not possible, right? You must come back to the ground state manifold in the middle. So the only contribution that can come is from the second term, right? Where you go to the excited states, come back to the ground state, then go again to the excited state, come back. So that's the only one that matters. And somehow that's sort of, roughly speaking, the square of the OGP, right? So we can write that down, square of the second order Hamiltonian. So what I'm saying is 1. So the only terms that can contribute come from this formula. And this is basically the square of the second order effect. So you just get another contribution, which is an exchange, but now you've done, so you get a term which is basically proportional to that. But it comes in with the opposite sign because the exchanges are different. And there's an extra minus sign there that accounts for it. So you get a contribution to H4. So one contribution is so this kind of reduces the leading exchange by some. Now the important thing is that you can also imagine having disconnected pieces that involve a bond here and a bond there. And those are zero because the effective Hamiltonian in the end has to be extensive. You can't have a double sum over all bonds of the lattice. And so if you did the full calculation, you must find that it cancels. And in the tutorial, that's an exercise for you to prove this linked cluster property of this expansion. That you never get terms that involves some cluster of spins here and another cluster of spins somewhere else. You never get that. Because if you got that, you will have a double sum over the locations and the energy would not be extensive, it would scale as a higher power of volume. So you can check very easily that that doesn't happen. So we are not going to do that. That's something you can check. So there's no terms that are disconnected. There's things that involve one bond. Then there's things that involve a site that talks to two different spins, like this. On the lattice. Anywhere on the lattice, if you have this motif, there will be a contribution. And what this does is it generates for you couplings that are next nearest neighbor on the lattice. So you can work that out. And I don't think I'll go through that in detail. And the final kinds of terms you get, so that's two bonds. And the third term, which is the most interesting, is four bonds, which involves a square plaquette of the lattice. Okay. So again, by the same logic we used when we looked at triangular plaquettes, the only way you can make this happen is if all four bonds correspond to appear in the effective Hamiltonian in a way that corresponds to fully clockwise motion or fully anti-clockwise motion. You've got to again sit and classify all possibilities for things to go around this way or that way, count particle exchanges and keep track of it. And again, you should sort of make a judicious choice of amplitudes to calculate from which you can reconstruct the whole effective Hamiltonian. So you can easily check, so this I've done, I'll just tell you what are the amplitudes you need to calculate. So you should work out the following independent amplitudes. So this is the alternating state on the plaquette. You work out the amplitude A to flip all the spins. Then you can work out the amplitude A prime to go from the same state to a state that you just exchange two spins. And the third one you do is you have one down spin and three up spins, and you work out the amplitude what did I do? Yeah, to exchange that. Okay. So there's two kinds of exchanges. Sorry, this one. Yeah. Yeah. So if you work these three out, you can work out the coefficients of the fourth order ring exchange. I times similarly for the third order and the second order. So knowing these three amplitudes, you can reconstruct all the coefficients, and this is what you will do in the tutorial, I hope. And let me write the answer. Yeah. Yeah. So that simply says that there's two factors of the energy denominator coming from that place. So, the projector square is the projector anyway. So it's just two factors of the energy. So that's just, that part is just algebra. I mean, I can have some visualization in terms of amplitudes to go to excited state, but why you get a second power of the energy denominator? Yeah, it comes from the expansion, but he's asking for some physical picture for it. I mean, we are used to thinking of time spent in excited states and integrating over time and then getting one power of the energy denominator, but I don't know why you get it. So I hope I've sketched, at least to some degree of satisfaction, how you get the answer, and now let me write the answer down. So the bottom line is that on any lattice, the effective Hamiltonian is a sum of four kinds of processes. One of them involves just two spins, 1 and 2, coupled to each other by one hop. So this means it's a sum over all nearest neighbor links of your lattice. And that is this is the fourth order term that subtracts from the leading answer. This is just spin exchange. This is Heisenberg spin exchange. Then there's the coupling to the spin chirality. Then there is a term that involves, imaginary part, 6 times imaginary part, So, 6 times imaginary part. There. So that's the sine phi, more generally. Then all motifs of this kind, where you have a single side coupled to two other sides, you don't care whether there's a coupling that way or not, because it only involves these two ones. And implicit in this notation is the idea that you would count this twice, because 3 and 2 will get integrated, right? This generates next nearest neighbor hops, next nearest neighbor exchanges, which are also antiferromagnetic, so which compete with the leading one. And then there is the ring exchange. So this involves all 4 bonds, and it has many pieces in it. The first is the ring exchange. The second is all possible pairs, 1, 2, 2, 3. The third is identity. So this is the exact form of the effective Hamiltonian up to 4th order on any lattice, okay, which you can derive by this procedure. Now the reason I went through all this is to sort of provide some formulae that are background to some words I'm going to speak now. So this set of lectures is supposed to be about frustrated magnets. So what do I mean by frustrated magnets? Well, frustrated magnets are magnets where the leading exchange interactions in the system compete with each other or compete with other interactions that are also present in such a way that it's hard for the system to decide what's the optimal configuration it should have to lower the energy, right? So there's 2 ways in which this can happen. One is even if you are in a very strongly Mott insulating regime where the charge gap is very large, so that you can forget about all these higher order terms and just take this term, just the leading term. Just the geometry of the lattice, just the geometry of the nearest neighbor connectivity of the lattice can cause just this term to compete with each other, right? Because this is a sum over all links of the lattice, and you can ask what would minimize the energy of a Hamiltonian like that. And if you think semi-classically, you would just imagine that your spins are unit vectors that can point anywhere in spin space. And if you had a Hamiltonian that looked like, you would minimize the energy simply by saying every spin must be anti-parallel to all its leads, right? So if I have a up spin here, it must be down, 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 down. On a square lattice, for example, I can do this, right? On any bipartite lattice in general, I can find the global minimum of this energy. It's achievable. And it's simply you divide the lattice into A and B sublattices so that the links are only going from A sublattice to B sublattice. You pick some random vector in spin space spontaneously, and all the spins on the A sublattice point along N, and all the spins the B sublattice point anti-parallel. This will minimize it, right? But what if the nearest neighbor connectivity is such that there are triangles in the lattice, right? You can have paths of length 3. You have a site 1, 2, 3, like that. Clearly, it's not possible to have any state like this now, right? And what state gets chosen then depends on how these triangles are tiled to make the whole lattice. Right? If you just had 3 spins talking to each other like this, there's another obvious thing you can do. You can pick any plane spontaneously in spin space, and on any plane you could point them 120 degrees apart. That would be a minimum, right? So this involves a spontaneous choice of plane and then an choice of direction in the plane, right, to minimize it. But this is not always possible. It depends on the whole lattice. So just the geometry of the nearest neighbor connectivity can make these leading exchange interactions compete with each other, at least at this classical level. And that's the most dramatic effect of that competition sometimes, is that the leading exchange interactions are completely unable to decide what the lowest energy configuration is. There's a huge degeneracy still left over after you've taken the leading exchange interaction. And whenever you have huge degeneracies in physics, there's opportunity for new physics. That's the whole point of stories like the quantum Hall effect rely on the fact that the biggest term is the kinetic energy, but because of Landau level quantization, it's completely quenched. So then all the physics is the physics of how that huge degeneracy is split. Right? The same thing can happen here if the geometry of the lattice is such that it makes these terms compete amongst each other. Right? But that's not the only way frustration can come into the system. That's not the only way. The simple nail state, which is one half of the system pointing up, the other half pointing down along some axis, the nail state. That's not the only way this can get destroyed. It can also get destroyed because the charge gap is not very big, and although it's correct to think in terms of spin physics and forget the charge degrees of freedom, virtual charge excitation are important enough that they contribute terms like this and terms like that. Right? And these have completely different preferences in terms of their semi-classical configuration. So, for example, this term, it favors a definite chirality. So it would like to take three vectors which are all right-handed or left-handed depending on the flux. That make a right-handed triad or a left-handed triad depending on the flux. Right? This term, it has some complicated behavior. It's actually it's the ring exchange of four particles. I didn't define it, but the notation is obvious. It's the term that takes these four labels and permutes them like this. Right? And the other one. So what this favors semi-classically is a different story altogether, and it's not the nail state. For example, it's known that if you had a triangular lattice, I need to draw this better. If you had a triangular lattice, it's known that if you had this alone and you didn't have the exchange term at all, then its energetic preferences, thinking of it classically, are to make not this 120 degree state. So if you had a triangular lattice and just had the nearest neighbor exchange, then you would just say that the triangular lattice is a three sublattice structure, A, B, C, like that. And you would randomly assign the A's spontaneously to point along some direction, all the A spins in some plane. All the B spins would point along that direction, and all the C spins would point along that. That would minimize gain. Right? So this is called the 120 degree state, and it's actually the ordered ground state of the triangular lattice Heisenberg. But at 0 time. But you can't have this happen if you have just ring exchange. And what the system prefers to do is to take a 4 sublattice decomposition. So you kind of tile this lattice with 4 sublattices, A, B, C, D, like that, into disjoint plaquettes. The next plaquette is A, B, C, D is here, like that. You do that, and the spins like to point along corners of a tetrahedron. So one spin points like that, one like that, one like that, one. That's the minimizing. So the point is that both sort of higher order exchanges and competition between the leading order exchanges because of geometry can destabilize these simple patterns that one can work out easily, like the nail angle. And more importantly, they can lead to large degeneracies at low time. And then the interesting question is how these are resolved, what are the states that are saved? And that's sort of the subject of so that's roughly where I wanted to stop. Good, on time I think. And so in the tutorial, I think part of the time I'd like to suggest that some of you can try and actually work through the calculations I've sketched. I'll be here. We can work through some of the details. And part of the time, Shubhro Bhattacharjee will explain how even more exotic spin Hamiltonians arise in the presence of spin orbit.